which will be held here at the State Library of Queensland from the 19th to the 22nd of May. The Deepen the Conversation program is a series of talks, debates and conversations with leading thinkers designed to share and stimulate ideas. The Ideas Festival 2011 will feature an innovative and interactive program focused around the themes of food futures, sustainability and happiness. This evening, we are pleased to welcome Mike Duggan to facilitate this exciting discussion. Mike is the General Manager of EcoSpecifier. He co-founded the sustainability consultancy company, FWR Group, and has been significantly involved in the development of the University of the Sunshine Coast Sustainability Research Centre. Joining Mike in tonight's discussion is Professor Hal Gurgenci and Dr. Doon Wyborn. Professor Hal has been working in the area of mining and energy research for nearly 30 years. He's the Director for the Queensland Geothermal Energy Centre of Excellence at the University of Queensland, where he also lectures. He is also a member of the Executive Committee for the Australian Geothermal Energy Group. Dr. Doon Wyborn is an international research specialist in the area of geology. He has worked on the potential of enhanced geothermal systems, geothermal energy, since 1992, as recognised as the leading Australian authority on this subject. Doon was founding director and executive director of Geodynamics Limited and is currently its chief scientific officer. Before we start, may I please remind everyone to switch off their mobile phones and to also use the back exit if you wish to leave during the talk. We are audio and video recording this talk for the library website, so if you have any questions regarding that, please come and see myself or any of the library staff following the event. Following our In Conversation part of the event, there will be an opportunity for audience questions. There will be microphones handed around for these questions to be heard. Please join me in warmly welcoming Mike, Hal and Doon.
Well, good evening, ladies and gentlemen, and welcome to tonight's Deepening the Conversation, Harnessing Heat. I'm very lucky to be joined by two eminent experts in the area of geothermal energy, Hal and Doon. There is no doubt, really, that energy is the biggest business that there is on Earth. It's gone through amazing changes coming from the drivers of pollution, climate change, renewable electricity, and finance. But the question that we really have to ask ourselves this evening is, do we trust in Rocky? In rock, we trust. One of the guests that wasn't introduced this evening by Emma is our lovely inanimate chunk of carbon and rock. How deep did this gentleman join us from?
About 2 or 3 kilometres, yeah.
About 2 or 3 kilometres, this little chunk of rock joined us from underneath the Earth and could be the answer. Could be, and that's debatable and something we'll discuss this evening, could be the answer to many of our energy mix problems or challenges. What I'm going to do first, I'm going to ask Hal to tell us a little bit about how geothermal energy works. You know, what the magic is behind and the science is behind geothermal energy. Hal, can you take us and tell us some more information about this?
Look, you all know the Earth has a hot center. So the geothermal is the heat of the Earth. You take the heat to the surface and you convert that to electricity. How do you convert that? You take the heat, you use that to boil a low temperature fluid. You drill a hole, the fluid, geothermal fluid, which is down there 5 kilometers deep in Doon's company's case. It comes to the surface, you take its heat away, use it to expand another fluid. It expands, you blow it across a turbine turns, generates electricity. You send the electricity away to whoever wants to use it. You send the fluid back into the Earth to be heated again, and just cycle repeats itself. That's the kind of geothermal energy that we are pursuing in Australia. There are different types in different parts of the world, but I think we stick to this one because that's really what we're interested in this country.
And Doon, obviously you've got a specific technique that you use. Can you tell us more about that?
Yes, the standard geothermal energy that's been pursued around the world for over 100 years, electricity was generated from volcanic geothermal energy in Italy at about 1902. But it's only been more recently in the last couple of decades where there's this new way of looking at getting heat out of the earth, and it's called enhanced geothermal systems. And in standard geothermal fields in volcanic areas, you basically only have to drill a hole, and there's steam associated with those volcanoes, and that just comes out of the ground automatically, and you can use that steam to produce electricity, as Hal says. But there are many areas of the world where the steam doesn't exist, but the rock temperatures are very high, and the idea is that you are able to pass water through those rocks, heat the water up, and then bring it back to the surface. So it requires at least two wells, an injection well and a production well, and these wells have to be spaced a certain distance apart, such that the time that you're actually mining the heat out of a body of rock. So over time, the rock will cool, and it takes hundreds to thousands of years for the heat to come back. So in the sense of our timescale, it's actually not renewable, because you're actually taking the heat out of a body of rock and then you have to move elsewhere. And the trick is to make that heat last long enough such that a power station will pay itself back. So we typically think of about 30 to 50 years lifetime of a system. And because of that, the injection well and the production wells have to be something like a kilometre apart.
Now, perhaps, you tell us a little bit more, Hal and Dune, about why we should bother. Maybe we'll run that little animation that Dune brought along that tells us a little bit more about geothermal energy. But tell us, why should we bother? Don't we have enough natural gas and coal to really see us through our energy requirements?
That's a good question. That's a very good question. I'll probably take that, and then you can add to that, Dune, afterwards.
Sure.
Why should we bother? I think if we are not concerned about burning coal or burning fossil fuels, I don't think we should bother, because geothermal, I don't think it's going to be cheaper than the present cost of coal-fired electricity. But it is generally accepted that coal-fired electricity has other external costs which are not really reflected in the busbar cost of the electricity. If you take those external costs into the picture, then people start looking for alternatives to fossil fuel electricity. Now, when you look for alternatives, then there comes into the picture renewable electricity. In amongst renewable energy alternatives, geothermal is the cheapest form of renewable energy alternative. In fact, I think Dune said that that's not exactly renewable. In the scheme of things, nothing is renewable. Even the sun is going to die at some stage. But it is whether we have enough resources of it. In terms of this geothermal, we have ample resources, enough enough hot rocks under the surface to last the country for thousands of years, whichever way you cut it. So I think, as far as I'm concerned, that's renewable.
Yeah, Hal, there was some research done by the US government in the late 70s where they actually looked at the total amount of fossil and fissile energy available to us, to the whole world, and also the amount of heat that was trapped in the earth in the depth from 3 to 10 kilometres. And it turns out that the amount of heat in the world's continents that's trapped at that depth is 10 times greater than all of the fossil and fissile and fast breeder reactor uranium that's available in the world. So here we have a potential energy source that's huge, and in fact we're not actually consuming very much of it at all at this stage. And basically we don't really want to get into the climate change arguments here, but if people want to reduce carbon emissions, then geothermal is base load, and it's the only alternative to fossil fuels that there's actually base load apart from nuclear.
In fact, I think that base load, if I may, is important operative word. Base load means it is on 24 hours a day, 7 days a week, 365 days a year. So it is on all the time unless something gets broken. And the geothermal power plants have a good pedigree on that. The capacity factor, which is the amount of time they are on, is better than 90% and better than other power plants. That's the existing geothermal practice. So in that case, you need some electricity being generated all the time, not dependent upon the vagaries of the nature. And coal-fired power plants are doing that. Nuclear plants can do that, are doing that, and so can geothermal. But there are not many other alternatives which can do that. I think that's, so baseload is an important word. Baseload means it is on all the time.
So it's baseload power. We're going to have a way to get it to people's houses, aren't we, and to people's businesses. What's the cost going to be? How are we going to transport this energy around?
Yeah, the grid system is in place for much of the electricity use that we take for granted now. But in our case, we're actually operating, trying to establish a production system a long way away from the grid, and it's definitely quite a conundrum that we have to face, that we have to get that energy to the grid. And we've looked at, but the reason why we're actually persisting with this in the location I haven't explained, but we believe that the location that we're working in northern South Australia, in the middle of the desert, is actually the most ideal place in the world for commercialising enhanced geothermal systems. I haven't spoken much about that yet. I hope we have the opportunity to talk a bit about how we do this enhancement. But this area in Central Australia, even though it's a long way from the grid, it has the potential to provide Australia with a very large fraction of its electricity requirements for the next 100 years, perhaps in the order of 25%, just from this one small area. And of course it may well be the best area in the world, as we claim, but leading on from the development in such an area, there'll be other areas that will be able to come on stream that are perhaps not quite as good, and hence there's the potential for enhanced geothermal systems to provide a very large fraction of Australia and the world's energy production. And in both Europe and the United States, there's quite a lot of interest and a lot of support for developing these systems. And I think in our case, because we're a long way from the grid, it's because of the large scale that the grid will come.
Come to you.
The grid will have to come, yep. Okay. And there are some advantages in our location, because the grid in southeastern Australia runs from Cairns down to Victoria and then over to Adelaide. It's kind of like a big banana, and we're out there in the middle of it. And if you connect up from Adelaide north and from northern South Australia east to Brisbane, then you end up making a loop rather than a single long string. And that loop actually improves the efficiency of the grid. So there are benefits related to that can justify the building of a network into this location where huge potential exists.
Okay. And Hal, what are your thoughts on enhanced geothermal energy? Is there some challenges, technical challenges, or?
There are technical challenges. I think I would hate the audience to leave this saying that this is a done deal, it's all done. It is not. It has great potential. I think it has the greatest potential of all the renewable energy alternatives we have. But at the same time, it is not a done deal. I think you probably get some of from what Dune is going to say about the enhancement technologies. Australia is a leading player in this area in this particular form of geothermal energy. In fact, Dune's company, Geodynamics, and I may say that because I'm from a university, Dune's company, Geodynamics, and another company, Petrotherm, which is in South Australia, they are probably the leading companies in the world in terms of commercializing this form of geothermal energy, and a lot of people are looking into what's happening here. Now, in terms of challenges, I was in a workshop in California a month ago, and three things were raised in that meeting by ExxonMobil, by Department of Energy, and by other companies. So they were almost speaking of the same book, and those three challenges were A, 20% reduction in the cost of drilling, doubling the flow rates, that's the flow rate coming out of the geothermal well to the surface so it can generate power, and 20% increase in the power conversion efficiency. So these are significant challenges. I can speak for the third one. I think that's the challenge we can solve in the next 5 to 6 years. In fact, that's one of our aims of our centre. I'll let June to talk about the flow rates.
Certainly, that's one of our challenges is improving the flow rates from each of our wells and improving the capability of injecting that produced water back into the reservoir. And we still have quite a way to go to make that work, but we certainly have learnt a lot from what we've done so far. To give you an idea, the flow rates that we're getting from our production well currently is around about 30 litres a second, and that's something like around about 10 megawatts, and the temperature is over 200 degrees C. That's around about 10 megawatts thermal, which will produce around about 3 megawatts, 2 to 3 megawatts electrical.
With the existing technology?
With existing technology. Hal's going to improve it by 20%, yes, so that'll
about
help.
50%.
50%?
Yes.
Well done, Hal. Well, hopefully we'll be able to improve our flow rates by 50% too.
You heard it here first, ladies and gentlemen. Please don't call the Courier Mail quite yet.
Yeah, so, we're getting around 30 litres a second, and we want that to be up around 70 or 80 litres a second out of an individual well, and potentially something like 8 to 10 megawatts per well. And that's a lot of, if you think about the scale of the system, we believe that we can ultimately produce tens of thousands of megawatts of EGS. In our particular area, something like 6,000 to 10,000 megawatts of EGS. And if you can get 10 megawatts per well, that's something like 600 to production wells, and then you need all the injection wells as well, which is almost double. So we're talking about 1,000 or more wells to be drilled, and each one of them is in the order of $20 million in cost. So it's a big project. And then you've got to build the power stations. The power stations are the drilling costs and the power stations costs are roughly equal, I would say.
That's true. Yeah.
So Google just invested how much? $100-odd million or more in this type of technology in the US?
Not quite that much yet.
Not quite that much?
No, but they're very keen on this process, and the little animation that you saw just a while back was actually an animation that was produced by Google on our project in northern South Australia. And they provided that gratis. Also, another thing that they did is they improved the Google Earth resolution of their satellite images across our exploration licence areas, which was very good of them at no cost. They were very keen to actually invest in our process or in our company, or at least help us out. But because it wasn't in the US, they've gone to the US and they're actually spending, I think they've spent around about $10 million so far in the US on 2 separate projects.
Okay.
Just on the US, the US Department of Energy have actually allocated around about $600 million to geothermal research over the next few years, and around about half of that is in enhanced geothermal systems. So there's strong recognition over there, and also in Europe for the potential of this new energy source. And part of the reason for that is that a group of experts got together in about 2005, led by Professor Jefferson Tester at the Massachusetts Institute of Technology, Chemical Engineering Department. And they basically looked at enhanced geothermal systems, or EGS, as the way of the future, recognising that we have to break the carbon fossil fuel link. And they produced this book, which I have here. It's called The Future of Geothermal Energy. And you can download this whole book free from the web if you're interested. It's, if you type into Google MIT for Massachusetts Institute of Technology and then EGS, you'll find there's about 10 chapters, and each chapter can be downloaded individually, or you can download the whole book. And and in this book, the proponents advocated that the US government spend something like $800 million to $1 billion on EGS research over the next 15 years. And as a result of that, they predicted that by 2050 there'd be around about 100,000 megawatts of electricity production on stream in the US from EGS. And these numbers may not mean anything to you, but 100,000 megawatts is around about 3 times Australia's electricity requirements at the moment. So 3 times the size of Australia's electricity requirements from EGS by 2050. And the way they put it with this 800 million to $1 billion worth of research dollars, they say that that's equivalent to a small carbon capture coal-fired power station in cost. So definitely worthwhile. And the Department of Energy is actually coming to the party with about 400 million so far.
I think it is very important, I think, to emphasize the point that this is EGS. And I want to emphasize that because I don't want that point to be missed either. Because when you talk to people about geothermal energy, the first impression is it is old hat. It has been around for a long time. North Italy, Lardarello had it in 1910s. New Zealand had it for a long time. Japan has had it for a long time. Tuscany is producing 25% of its energy, electricity from geothermal. Iceland has been producing almost all of its electricity from geothermal resources for a long, long time. So the question can be asked, okay, what is it so new about it? Why are we talking about it? The question is, that's a type of conventional geothermal energy in which you drill the well. As you drill the well, like an artesian spring, the hot water or hot steam, depending on your reservoir, comes up. All you have to do is run it through your turbine and produce electricity. Unfortunately, that type of geothermal heat is not everywhere. It is only in those places which happen to be near the volcanoes or near where the continental plates are joining. And Australia is not one of those areas. So, and that type of geothermal energy was reaching its limits. And there are still, it will expand it probably linearly every year by another 1,000 megawatts. But that's not going to be the solution to the Earth's electricity problem. That's why it was very exciting in 2006. This panel of scientists came out and they said, hey, hold on a second. That geothermal is only a fraction of it. What we have, if we go deeper to 5 kilometers, wherever we drill in the world, almost, not quite, but almost, we'll reach hot rocks. Then it becomes a ubiquitous source. It becomes so abundant, then, that's what they used to say in the 1950s for nuclear energy. You don't have to meter it. And this is true, well and truly like that. You won't have to meter it. It is everywhere. It is not scarce. But the thing is, it does have significant challenges. It is a new form of energy. It is a new type of energy. It only started in earnest in the last 4 or 5 years. That's why it has challenges. So these are not challenges which has been for age long for many, many years. We're just facing those challenges. I'm confident we'll solve them. I just want that to be clear.
And the other one that you mentioned is drilling costs.
Yes.
And in fact, drilling costs, there needs to be a step change in the cost of drilling to reduce costs. And there are a number of technologies that are being researched, things like sporlation drilling, where you, rather than using a conventional oil field drilling rig, you actually break the rock apart with heat. You can pump things like hydrogen and oxygen down there and burn it underwater, and that makes the rock spall and turns into powder, and then you pump with the water, pump the powder out to the surface. And there are other new bit technologies that are coming on stream that can improve the rate of penetration of a drill bit by perhaps 5 times. And things like that are going to make things... the oil industry aren't really too interested in improving drilling techniques like we are.
Just on that note, June, you would know that there is nothing new in the world. That sort of drilling was how Romans used to drill, by heating it and then putting just cold water on it, just by cyclic heating and cooling. And it used to take at that time a very long time. Now, this thing is going to go just like that very quickly. That's the difference, but the same technology.
Yep.
If you take one quote away from this evening from the gentleman speaking about Google, of course, Dune was... Do you remember that quote?
Which one was
the killer app?
Oh, the killer, of course, yes. As you came in earlier on, before 6, there was a little interview being shown, and that was an interview with Stephen Chu, who's the US Secretary of Energy, who is promoting enhanced geothermal systems, and Dan Riker, who's the Google Director of Climate Change and Energy. And yeah, he was calling it the killer app, of course. Sorry.
The killer app of renewable energy.
Yeah.
Yes, it is a quote for...
of energy, not just renewable.
Of energy.
Yeah,
of energy.
Killer app of energy.
So we've talked about challenges technically, we've talked about economics. What about social challenges? Or social opportunities that are going to spin off perhaps from the geothermal energy industry?
Yeah. Of course, with all energy production, people will challenge you in terms of potential environmental issues, and there are some. And I don't know whether we need to talk about them now, but certainly if anybody in the audience wants to ask particularly a question on the environmental challenges that might beset us, that's fine. But I think the advantages that we have here is that if we can produce electricity as base load from non-fossil fuel sources, then the industries that are energy intensive, like perhaps aluminium refining and even the data centres, computer data centres are another energy-intensive requirement that requires energy, and they're looking, and this is why Google is actually interested, because of their requirement for large amounts of energy to store data. These kinds of things, these kinds of businesses will come to Australia and to the locations where this kind of energy is available. So even though the actual process of generating the energy doesn't produce large numbers of jobs, the spin-offs of new industries will produce large numbers of jobs and be good for the country.
Sorry, Hal, go ahead.
Just on that, jobs will be generated, but in different forms. Because if you look at it, it is the price of the electricity, let's say, will be 9 to 10 cents per kilowatt hour or whatever up to that. That's all going to go to jobs someplace. Either the jobs of the people drilling the hole, or the jobs of the people manufacturing the turbines, or jobs of the people manufacturing the cooling towers. So there are going to be jobs. There are going to be a large number of jobs across the world. Now, if Australian manufacturing industry will be able to capture some of that, I think we'll have to see. But I'm hoping that it's one of our missions as the Queensland Centre to make sure that at least a part of that action is taken by the Australian industry. If that happens, then there's going to be a large number of jobs, not only in drilling and preparing the land, and also producing the equipment for the planes.
So we've got... do you have anything to add to that, Dune?
No, but I was going to talk a little bit about what this enhanced means in geothermal and use that piece of rock there as a to describe it, if you wouldn't mind. What we have in many places in the earth are large bodies of granite that are very homogeneous in their rock properties. This is a piece of granite from a drill core, And this has got a fracture running through it. Now, granites have, and most other rocks too, have fractures running through them. And if you try and pass the water through that fracture, you find that it's so tight that it won't move through. And the enhancement in geothermal is actually making that fracture slip a little bit. And you won't be able to see it from the audience, but if I make that fracture slip just 1 millimetre or 2, then all of a sudden there's a much bigger space inside the fracture, and that larger space is what allows the water to flow more freely. Generally, the movement of this fracture by 2 or 3 millimetres will improve the conductivity of fluid through that fracture by 2 or 3 orders of magnitude, and that's enough to make this potentially economically viable. So just this one little bit of rock and the slipping of that fracture is the basis of enhanced geothermal systems. Now, when it does move, you end up causing what's called a microseismic event. And in that animation that you saw on the screen, there are a whole lot of dots, and all of those little dots represent a microseismic event that was picked up during the movement of the rock. And how do we make the rock move? Well, we pump in pure water, nothing but pure water. And when the water pressure along the fracture increases, it's in a triaxial stress field, and as a result of that, the fracture moves a little bit. It's essentially a micro-earthquake, and all of those little dots represent micro-earthquakes. So we can, not only do we know that we're improving the conductivity of the rock by making these earthquakes, we can also follow where the process is going on, and therefore we can use that to dictate the size of the reservoir and how far away we can need to drill the other well, and what's the best location to drill the other well. So we could, when we stop doing this, when we've already got the reservoir grown out, say 1 kilometre, then we stop and we can drill the other well. So it's a technique that has been really perfected by a number of projects overseas, but we've been more successful in any of those projects in our site in Central Australia. Thanks.
Thanks, Dan. Has there been anyone internationally that's been able to commercialise to a significant degree this type of technology?
There are a couple of projects in Europe where they're generating several megawatts of power with 2 or 3 drill holes, one in France and one in Germany, and there are more projects going on in Germany, but they have rather different conditions whereby it's hard for them to scale up the way we can scale up in Australia. The reservoirs that they generate there it's actually in the Rheingraben, which is kind of like a rift valley, and the rock is falling apart with steeply dipping faults as it falls apart, and the reservoirs tend to be oriented vertically, and so they can build a little reservoir in one place, but they can't link it to another reservoir, so they have to go somewhere else and make another one. And so their hope is to make many small ones. In our case, we're kind of held in the vice grip of a large continent, and also that the stress conditions are such that being held there, the fractures that are relatively horizontal are the ones which take the flow. And so we end up making these pancake reservoirs, and they can be spread out in the hot rock, and so you can drill many holes into that reservoir and expand it up, and then continue expanding it in different directions. And that's why in this kind of condition we can potentially build very large systems, much larger than the ones that have been already developed in France and Germany.
Wonderful. Now, Hal, just as a question generally, we've talked a lot about quite a significant amount of issues this evening. What do you see as being, I guess, some of the future of this particular industry? Crystal ball gaze for me, what do you see as being something that's going to occur in the next 5 to 10 years?
Well, the Electricity Supply Association of Australia, I think, has projected with several provisos that this type of energy could provide up to 10% of the country's electricity needs by 2030, I think it was. And similar numbers, 10% of the present American needs. That was the purpose of the $500 million investment by Obama administration 2 years ago, which is still going on in terms of the research projects. The objective of that is to generate up to 10% of the present electricity generation of America from deep geothermal or enhanced geothermal systems, or EGS as Duane was calling it, by 2050.
Yeah, it was 100,000 megawatts, which is 100 gigawatts in the US by 2050.
That's correct.
Yeah, and the electricity requirements of Australia are around about 30 gigawatts, so this is like 3 times Australia's requirements in the US by 2050. And if they can do it, we've actually got better resources than they have. We should be able to do it too.
Anything else you'd like to add to that, Duane, in terms of your crystal ball gazing? You, as an insider, what do you see happening, without giving away any trade secrets, of course?
We need government support, and we probably need a carbon tax or some price on carbon. But there has been government support. Our company has a $90 million grant from the federal government's Renewable Energy Demonstration Program, and we're using that $90 million in developing what we call our first commercial demonstration plant, which is a 25 megawatt power station with 6 drill holes associated with it, somewhat similar to the animation that you would have seen. And the first of the wells, of those 6 wells, we'll be starting to drill later this year, and we're hopeful of having that power station up and running by 2015. And we need to improve the flow rates per well to generate 25 megawatts, but we have a good understanding about how it'll work, and we think that we can achieve that.
Wonderful. Well, we managed to get through 45 whole minutes without mentioning the word carbon and tax together in one sentence. So that was fairly effective and good. I'm sure that will have elicited a few more questions from the audience, which is great. Look, we're coming towards the session, the part of the session where we'll be asking you to ask us some questions. What I thought I'd do, and with your permission, Duane, is as a way to do that, we'll could pass the rock around and people could take a peek. But there is
It's got to come back here at the end.
So no one leaves the room without being strip searched if the rock disappears. So. And I'm not volunteering to do... Emma, you're going to have to hand it out. Fair enough. So what I'll do is I'll move up in there and pass the rock. What I'd love to do is I'd love to get... there's people with microphones out to the left and to the right of the auditorium. If I could get you to just raise your hand if you've got a question. Now, as you're getting the microphone brought over to you, please make sure that you keep your questions fairly concise as possible, so that we can get through as many as we can within the next 15 or so minutes. And that should give us just enough time for us to do our very first question. Lady in the red, please. Yes.
Hello there. I guess I'm more interested in the environmental impacts of it. So if you could probably talk about that a little bit, that would be appreciated. And I guess I was curious about whether these kind of developments are done in confined aquifers. Is it in the Great Artesian Basin? I'm not quite sure. So, yeah, those kind of issues I'd be interested in hearing a bit more about.
Yeah, thank you for the question. Certainly, people have raised a number of issues, environmental issues, about our potential technology. They include where does the water come from, radioactivity, are we damaging aquifers, and also is there any potential for larger earthquakes that may damage surface installations. We believe that we can answer all of those questions. First of all, in fact, the locations where we're actually operating are completely and utterly unrelated to aquifers that exist that are usable by... we're deeper than that. We are not connected to, say, the Great Artesian Basin. We actually have to drill through the Great Artesian Basin, but we case that off. And in fact, if the casing connected, or if we had a break in the casing and it connected to the Great Artesian Basin, we would have to write the well off. So we're definitely not connected to the Great Artesian Basin. We're much deeper than that. And the water systems that we're creating are completely isolated and not related. In fact, it's been proposed that you can actually inject radioactive waste into these holes after the heat's been taken out, and you can be guaranteed that it'll be there for the next 100 million years. So these areas are not directly connected to any areas where we're concerned about the environment. It's also closed loop, so we're not bringing anything out to the surface. At the surface, there's a heat exchanger, and through the turbine, you're passing actually distilled water, and the water that comes out of the ground is re-injected. There are some salts and things in that water, but none of that comes to the surface. If there was, say, a breach of a pipe at the surface, then within a few seconds the systems would be closed off with emergency shutdown valves, and only a few litres of water would leak out onto the surface. So the footprint of these systems is actually much smaller than virtually any other kind of energy production, because for a 50 megawatt power station, which is sort of the next stage up from our 25 megawatt commercial plant, we're looking at a footprint of about 200 metres by 200 metres on the surface, and even though the wells spread out to several kilometres down 5 kilometres deep, they're all come to the same point on the surface. So the footprint is very small.
Yes, now the question up there, yes.
Good evening. Obviously there's a number of different technologies vying to be the effective replacement for coal-fired energy. Can you objectify where you are relevant to other technologies in the race, if you like, for that position, both here in Australia and also perhaps internationally?
Your turn.
I'll take that. In terms of installed capacity, there are two ways to answer that. One is the race means in terms of how far ahead, what is the installed capacity. I think the largest installed capacity in renewables is in wind energy. That's because wind energy can be taken in small amounts and can be built in where there is lots of wind. But we're probably approaching sort of the end of those good spots for wind. In terms of cost, if you put the coal-fired electricity, if you don't burn coal, the next cheapest form of electricity will come from natural gas. That's what my belief anyway. That will be like probably about 7 cents per kilowatt hour. After that, when you talk about renewables, this form of energy will produce the cheapest electricity. But the reason it hasn't caught on so far is A, it's not a done deal, as it's a new form of energy, and B, it is not something you can take in at small scale. You cannot put a couple of panels on your roof and produce geothermal electricity. Yeah, it requires a substantial investment. That's why it is taking slowly. But when it is realized, and which will not be too long, it has the potential of generating the cheapest form of electricity from renewable sources, and for a very long time.
The MIT report looks at the coming down the cost curve, and they say that sure we're well above the cost curve for other energy sources like fossil fuels at the moment, But we can come down the cost curve quite steeply, and they claim that within 10 years of production commencing in the US, and after building around about $600 million worth of power plants and having around about 200 megawatts installed, will be cheaper than fossil fuels, than coal, even without a carbon tax. But you've got to come down that cost curve. But right at the moment, where PV is way more expensive, and obviously coal is way cheaper, we're somewhere in between.
How about solar thermal?
And we're probably cheaper than solar thermal already. And solar thermal that includes heat storage to extend the daily range of production. Definitely cheaper.
What about hydro?
Well, there just aren't many hydropower projects going on in the world now because they're too environmentally damaging.
There isn't a resource.
We've lost. Well, there's no resource much in Australia anymore, and in other parts of the world, they're not being developed.
In areas, countries blessed with hydro is the cheapest form of electricity, but there are not many countries like that.
Go to this gentleman in the front here, the microphone.
Given the tyranny of distance as far as where your site is actually concerned, on a cost-benefit analysis basis, is there anywhere closer to existing, I suppose, power lines where this site might be of high quality as your site, which might make it cheaper as the way off for producing energy?
Yeah, one of the issues, it's very clearly a major issue that we have, and other people have stated that getting close to the grid is more important than getting an ideal site. But the problems are underground in terms of drilling costs and flow rates and energy conversion because of temperature. We have our site is the highest temperature in the world in a non-volcanic environment, and it's spread out over more than 1,000 square kilometres. Anywhere in that 1,000 square kilometres, you can drill a hole and you'll find a temperature of 250 to 300 degrees at 5 kilometres depth. I think we've taken the position that trying to make it work in the most ideal location is the best thing to do, and then the other locations will come on stream later, and particularly because of the scale of the resource that's in that location.
This gentleman at the back.
G'day. Hello? Yeah. I was just going to ask a question. You said it was in granitic bodies and things like that. If it's basically two questions. Can it be done in sandstone, which is more porous and which can carry water a lot better than a granite? Because it's already porous, providing that it's not obviously at too much depth. And if you're going to look for these granitic bodies that are under the ground that can't be visible at the surface, aren't you going to waste a lot of money actually drilling to look for these sizable granitic plutons that have come up already to actually use as a source?
Yeah, well, the idea of tapping into aquifers like sandstones is actually not new, and it's been given a term lately called hot sedimentary aquifers, HSA. The problem with these aquifers is that the temperatures are nowhere near as high, and even if they were, as you increase the temperature, the recrystallisation of the grains results in a loss of porosity and a loss of permeability. The higher the temperature of a porous medium, the lower the permeability and porosity. And so you're fighting against that, whereas in fractured rocks, in hot fractured rocks or in EGS, and particularly in granites, it's already been proven that we can improve the fracture conductivity, and fracture conductivity is actually incredibly high in some granites, such that you even get convection in the location in France where they're actually generating power there. there's convection going on in the fractures in the granite, steeply dipping fractures. There's convection going on, and as soon as you get into the sedimentary rocks above, there's no flow of water whatsoever. So there is some potential for hot sedimentary aquifers, but not very great. And the other question...
To do with the actual drilling sites associated with it? Something you're looking at great depths. Has anybody actually mapped these areas before?
Yes. Yeah, buried granites. Yeah, the good thing about granites is that they actually form gravity lows. So all you have to do is take measurements of gravity on the surface. You can even do it in an aeroplane and even in the satellite. In fact, they're using satellite gravity now to determine the rate of ice loss in Antarctica and Greenland. But with gravity, you can determine gravity lows that are buried underneath the ground and use that to target these sites. But many of them are already known because there's quite a good gravity map of Australia already existing, and many of these sites are already known, and that's how come we know that this particular site, where at northern South Australia, at Inaminka, is potentially the best place in the world because a lot of these sites are already known.
Thank you. How easy is it to drill 5 kilometres through the core? You've had some drills being damaged, some not drills, some drill holes. How easy is it to do that?
Well, it's turned out not to be that easy, but we do learn, and in fact in the oil industry it's been quite well established that there's a learning curve in drilling whereby the first drill hole in any one area is generally around about twice the cost of about the 6th hole, because by learning you learn what kind of bits to use to go through what kind of formations, and every time you learn something new and you improve with the next well. We've learned a lot and we think we know how to do it now.
Is there another person up near the back that has a microphone? No? Down here?
My question relates to the economics and the social disruption of competition with the oil and gas industry, oil, gas and coal industries, and the fact that when these sort of power plants get running, then there's no ongoing revenue for the current billions of dollars that are being made by very powerful companies that obviously have a big effect on politics in Australia and other parts of the world. I see that as one of the major problems of this type of business getting off the ground. Can you comment on that?
I think you already commented on that. And look, it is well known that any disruptive technology is not liked by the existing technologies answering the same need. But that doesn't mean that disruptive technologies haven't come in the past. So I don't think what's stopping this technology is resistance from the other industries at the moment. It is more the technical challenges that I think we talked about and we are working to solve.
My question's about water. I know you spoke briefly about it before. I just wanted to clarify a few things. Firstly, how much is actually needed to fracture the rock? What happens to this after the fracturing? How much is lost to evaporation or for other losses after the steam comes back up? And does this eventually cause the reservoir to run out of water?
And where does the
Yeah. Well, interestingly, there's quite a lot of water in the rock itself. And we were actually surprised by, with our first drill hole, to find all this water. And we still don't fully understand where the water is located. But in order to fracture the rock, we do have to pump a certain amount of water into the rock, and we have obtained that water from the surface. We do have shallow aquifers that we take that water from, but it's not a very large amount. The reservoir that we've created so far that would be large enough to provide around about 25 megawatts of production has been created by using 40,000 cubic metres of water, which has come from shallow aquifers and from the local river when it's in flood. Once that stimulation or the fracking has taken place, then there's no more water consumption. The water goes around and round in a circle. Fortunately, where we are working, where there is also water in the rock itself, there is a fluid overpressure in the rock, in the fractures already, which means that we don't have any water losses underground. In places like in France and Germany, where there isn't this fluid overpressure, they do lose water underground. And the way they overcome that is they have to have two pumps. They have a pump for injection and also a pump for production. And so they maintain the hydraulics underground by pulling out the same amount of water as they put in. And then on the surface there's no steam at all because it's all kept in a closed loop.
Given you're removing a lot of heat from subsurface area, can you induce earthquakes in the future by shrinkage?
That doesn't actually produce earthquakes. What it does do is that it opens up the fractures to allow them to flow better, and so we can get the water through the cooler areas much faster. The earthquakes occur when you actually apply overpressure and make the fractures slip. During our stimulations, we've made many micro earthquakes, and some a little bit higher than that. But during our circulation and production, there's never ever been an earthquake.
Now it is just 7 o'clock now, however, I'm happy to continue if there's a few more questions. We've got at least one at the back, one down here. Gentleman at the back.
If this technology does get off the ground worldwide on a very large scale, and there is a lot of heat being taken out of the ground in different places, is there any sort of, is that going to cause any sort of problem taking so much heat out of the ground? I expect not, but is that something that's taken into consideration?
Well, the heat's already coming out. We're just intersecting it before it gets out.
And
there's a heat flow everywhere, which is measured in milliwatts per square metre, and it's coming out of the ground all the time and has been ever since the Earth started. In fact, one of the interesting things is that radioactivity has kept the Earth in a dynamic state. If it wasn't for radioactivity, then all of the continental drift, plate tectonics, mountain building would have stopped in the first 1,000 million years, and in fact the Earth would consist of no continents, everything would be underwater, and there'd be no humans.
And taking that extra amount of heat out, is it something that's taken into consideration?
Just if I can add that, if we cover all our energy needs from geothermal, all our energy needs, not only electricity, transportation, heating, etc., we will only, the Earth is losing heat every year, about 3 times as much as that sort of heat. So every year the Earth is losing 3 times more, maybe more than 3, but several, not orders of magnitude, but in that order, losing that much heat. So there is no danger. So it is being lost already, no matter what we do.
First, thank you for your very enlightening talk. Gentleman here got some of my questions answered, thank you. The one thing I'm curious about, I've got two questions actually. The first one, I'm curious about this reservoir, these fractures. Are they there? Are you creating these things somehow? And also, it's in such a big area. How do you get your convection in all this area? Is it just with pumps like you said before, or is there pressures? And the other thing, there was an interesting show, I think it was on the ABC recently, about a place you didn't mention in Kenya. But is that a different type of geothermal, as you mentioned before, or is it the same as yours? Thank you very much.
Yeah, in Kenya, it's in a volcanic area. It's in the Rift Valley. Yeah, that was Catalyst last week, wasn't it? But yeah, and I was so overjoyed with the guy who was the geothermal engineer. He was so passionate about his project because it was doing such a great thing for the Kenyan population. It was really wonderful to see that. Now, the fractures that we have in our rocks, they already exist. We can't create a micro-earthquake unless there's a fracture there to start with. We're not making new fractures. In the coal seam gas industry and in the shale gas industry, where they talk about fracking, they are actually making new fractures. We don't use the term fracking, we use the word stimulation. And what we're doing is we're stimulating existing natural fractures. And why are these fractures there? Well, a granite body that is often 1,000 cubic kilometres or more, very commonly much bigger than that, it was molten at one stage at around about 750 degrees C, and it cooled, and then as it cools it contracts, and then as it contracts it self-fractures. So all granites have got major families of fractures running through them in different orientations, and they're the fractures that we take advantage of in the stimulations.
Would we have an inefficiency ratio figure? Like
Power conversion efficiency?
Power conversion efficiency depends on the temperature of the geothermal fluid you're getting out of the ground, and it becomes really commercially feasible at 140, 150 degrees Celsius. But in Cooper Basin, you're expecting temperature as high as 260 or 270. In fact, you're finding temperatures as high as 270. The conversion for that in that temperature range would be changing from 15% up to 20%. No. Depending on the temperature range, for 150 degrees Celsius temperature resource, your efficiency would be down at probably 12-13%.
This is megawatts thermal to megawatts electrical.
Yes.
Yeah, a coal-fired power station is about 35%.
Okay, in terms of the efficiency and how much energy you have to put in, well, it is probably generating a lot more.
The pumping requirements, maybe 10% of the electricity we get out, and of course the heat is free once you've drilled your hole.
Yeah, 15 probably if you include all the other fans
the power station
and things
itself.
like that.
Yeah.
But for every 1 megawatt you generate, you would have to provide probably 150 kilowatts to run the pumps and fans and you name it. So in terms of that, it is efficient. I understood your question as a thermodynamic efficiency of how much heat comes out of the ground and how much of that is produced to electricity. That was the first numbers that I quoted.
Gentleman at the back, I believe.
Yes. With the heat at these levels produced through radioactive decay and the pumps operating in a closed loop, as you say, is there a danger of radiation buildup in the system, and if so, are there measures in place to deal with such issues?
We've tried to measure the radium, uranium, thorium and radon abundance in the fluids that's coming out, and there is a little bit of radon. There's no uranium, there's no thorium. there's a very small amount of radium, and the radon actually has a half-life of 3.7 days. The levels that we've measured are below the levels that are considered safe for drinking. So we don't believe that we have a radioactivity issue.
And just to add to that, some of those granites occur very close to the surface. The reason they are hot in Cooper Basin, not only because they are radiogenically decaying, but also at the same time they are covered by kilometers of insulating sedimentary blankets. Otherwise, the heat production is very low. It is like less than 100 microwatts per cubic meter or something of that sort, isn't it?
Yeah, the heat production is the radioactive decay of the in situ elements, yes. And it's around about 10 microwatts per cubic metre, yeah.
10. So
whereas
that's
a common rock is around about a tenth to a fifth of that, like 1 or 2 microwatts per cubic metre. But if you go and live in Stanthorpe, for example, the heat production of the granites at Stanthorpe is similar to what we have in the Cooper Basin, except we've got it buried 3.5 kilometres down, whereas at Stanthorpe it's right at the surface. And in fact, there ought to be concern about people breathing in radon in basements in places like that where relatively highly radioactive, granites are present at the surface.
Ladies and gentlemen, we have time for 2 more questions. We're going to take the first one down here, then we'll give the microphone to one more person. We've got somewhere ready to go, and we'll be able to finish off.
Just try to understand the water consumption that you'll need. You can't obviously rely on flooding rivers. And you mentioned you'd be able to get your water from shallow aquifers. Are they definitely not related to the Greater Teesman Basin at all?
The shallow aquifers are not, no. That's where we would get our initial water, but we're pretty confident that we will be able to get most of our water actually from out of the granite at 4 kilometres depth, because we can produce it to the surface and then reuse it. And we've already done this in that some of the water that we've taken out of the granite, we've injected back in as a stimulation water to make our reservoirs. However, there is actually quite a lot of water. The only water that we need is the water for stimulation, and that's a one-off process. Once the reservoir has been created, there's no more water consumption.
For 15 years, maybe.
For 50 years.
15.
15?
How long is the reservoir going to last?
Well, between 30 and 50 years.
Okay,
yeah.
30 and 50 years, okay.
Yeah.
Yeah.
On the stimulation thing as well, you were mentioning that there'd be fine dust that would come to the surface during that process?
No.
Or did I not...
Dust? No.
Or from the fracturing, from the microseismic
events? There's microseismic events which we can detect with instruments, but nobody could even know that it was going on at surface.
Okay. So nothing else would be coming to the surface?
Nothing.
As a byproduct
No.
of that?
Isn't your problem too much water?
Well, I haven't spoken about what we call the fluid overpressures.
No, the Cooper flood.
Oh, that water. Well, it is at the moment, yes. In fact, these... At Inaminka, Cooper Creek has got a causeway, and the causeway has been flooded with no access other than for about a week or two back in about August last year. But since March last year, the causeway at Inaminka has been flooded with no access at all across the causeway, and it's still 5 metres underwater right as of yesterday.
So I believe we've got one more question. There's a microphone out there somewhere. No? Okay. This gentleman right here is going to win with our last question for the evening.
About 6 months ago, I went to a meeting at the convention centre on the solar thermal presented by the group from the University of Melbourne, which was attended by the Premier and various other dignitaries. But unfortunately, and this is what concerns me, is that there's effectively been no publicity and no further development of this idea that we can see, although they come up with a plan which effectively made Australia independent of fossil fuel from about 2020 onwards. Have you guys been associated or know anything about that and how that would compare with what you're trying to do?
This is the zero carbon program, yeah. The people who looked at that did not take EGS into account when they were looking at zero carbon for Australia by 2020. I personally don't think that we're going to be able to achieve that. The government, there would just have to be a massive infrastructure cost involved in trying to do that. And I certainly would love to see solar thermal production happening on a large scale, just like we need geothermal. There is the government has provided quite a lot of money for solar thermal projects. I think a lot more than geothermal, in fact.
$7 billion for solar flagships.
How much?
Solar flagships.
$1 billion.
$1 billion.
Yeah,
yes.
I think it was $1 billion.
Yes.
Yeah. Yep.
Well, gentlemen, unless Dune or Hal, you have anything else that you'd like to add for the evening, we may say thank you very much for your time this evening. We certainly appreciate it as an audience.
Thank you.
Thank you.
I'd like to thank you, Mike, Hal and Dune, for providing us with insight into geothermal energy and sustainability. I have to say, to have such a level of knowledge on the stage is one thing, but to have it communicated it's such a complex issue to be communicated in such an accessible way is really valuable, I think, and I also have certainly gained a lot from this evening. So thank you very, very much for your time this evening. For information about our events held here at the State Library of Queensland, or to give us feedback on this evening's event or any other events, please visit our website or come and see any of our staff members here tonight. We hope that you will all come and join us for the Ideas Festival that will be here at the end of this month. Again, thank you all for coming. We hope you enjoyed your evening, and please once again thank the wonderful gentlemen that have joined us here this evening.
And I'm sure there'll be a rock out there somewhere that has a pleasant home back in Hal's bag on the way out. So, Emma, well, Christy, well done.